And it's our great pleasure to have Professor Bharat Ratra from Kansas University as our guest. Let me just tell you a few words about him. He is from India. He did his master at the University of Delhi. How do you? IIT Delhi. And then he did his PhD at Stanford, and then he went through a lot of prestigious places in the United States that I'm not going to bother you with, and he is now at the University of Kansas. He did a lot of important research in cosmology that part of which is going to be in his talk today. Again, I'm not going to tell you too much about that because he's much better for that, but one thing that I wanted to say is that he did close collaboration with Jim Peebles on things related to this and on things related to things that Jim Peebles eventually got his Nobel Prize for. So we have a person with Nobel Prize of degree separation of 1, which as far as I know is the best in Slovakia at the moment. So that's it, and Bharat, the floor is yours.
Thank you. Thank you very much. It's a great pleasure to be here. So I'm a cosmologist, and that means I'm interested in things that happen on very, very large scales. I study the universe and how things evolve in it, how they change in time. And it's a really exciting time to be doing this because we have great new telescopes both in space and on the ground and getting lots of new measurements. And we could be at the point where we're going to have a very interesting change in physics because some of these observations are suggesting that either quantum mechanics or general relativity or both need to be improved upon. So let me start here. This is just about 10 minutes away from where I live in Manhattan, Kansas, and it's tall grass prairie, and after summer, some of these grasses can be 10 feet high, like almost 3 meters. And it's a very nice place to go hiking. So I have questions for all of you, and you can put up your hands if you can answer them. So how many of you have gone hiking 10 kilometers in your life? What about 100 kilometers in your life, all together, integrated? 1,000 kilometers, 10,000 kilometers, 100,000 kilometers. Okay, so there's an upper limit to which you can go. I mean, if you had a lot of time and you lived long enough, you could go maybe 100,000 kilometers or so, maybe 10,000. Okay, the next thing I want you to do is I want you to reach up and grab a strand of your hair and feel it between your 2 fingers, at least those of you who have hair. So is that kind of the limit to which you can feel something small enough, smaller? Do you think your fingers are sensitive enough to feel something smaller, or is that kind of the limit? I mean, so that's kind of the limit. So if you have typical hair, it's maybe 100 microns or so in diameter. If it's thin, it could be 10 microns. So I've got a bunch of length scales up here in meters. So maybe 10 to the 5, 10 to the 6 meters is the distance to which you can walk. And you could get down here maybe to 10 to the minus 4 meters or so with your fingers. So these are kind of the regions that are directly accessible through your senses. But there's a lot of stuff going on much, much larger lengths and much, much smaller lengths. And it's really interesting to think about how you build up intuition over here compared to how you build it up over here and here. Excuse me, I've been talking too long, I think. So what you do over here, if you're very, very clever like Newton, you can collide 2 balls on the floor, or you can drop an apple, and eventually you'll figure out conservation of energy and momentum, and you can figure out the inverse square law for gravity. But you can't do that over here and over here because you cannot directly access those through your senses. And what you do over here is you basically collect light either using a telescope or a microscope or a particle accelerator. You break stuff up and you collect signals. And you store those signals in a computer as electronic signals. And then you build mathematical models. and you try to make predictions for those phenomena. So if you're studying like a star, you can decide what the composition is, the chemical composition, and you can heat it up and you can see what kind of light it would emit, and then you compare it to the light you've got stored in your telescope as an electronic signal. So the way you build up intuition over here and build up intuition over here is fundamentally different from what you do over here. And yeah, I guess the point was I'm going to make, I mean, you have these cards on your table, you're welcome to have them. And they're about global warming, and they connect to a really nice website that has a nice bunch of videos explaining global warming. And to understand that and appreciate that, you've got to understand that there are atoms and things out there, and that's really not directly accessible through your fingers. And the same thing's true over here. So there's no guarantee that the intuition you build up over here is going to work over here or over here, and actually it doesn't, because Newtonian physics doesn't apply on very large scales or very small scales. And what you have to do here is use general relativity, and you have to use quantum mechanics over here. So that's kind of an important point to remember. So I want to step out from here and get out to very large scales. And we'll start with this guy who you probably recognize. Instead of using length scales of meters, I'm going to work in Einstein's. And an Einstein is roughly 2 meters. So I don't have to do this just with length scales. I could do it with mass scales or time scales, but we don't have enough time here to do that. But there's 2 very nice videos you can search for on your favorite search engine. One's called The Powers of 10, and it's by the Eames brothers, a bunch of 2 architects. And there's an updated version of that from the American Museum of Natural History. They're both really nice videos. They're pretty short, and they give you kind of good summary. So if you're interested, you can look at that. So what I'm going to do is I'm going to jump here. And a picture like this has only been possible in the last 60 or so years since we've had satellites out in space. This is Africa. And one way to compare this is to build a tunnel from the North Pole to the South Pole and go and buy 6.5 million Einsteins and put one at the South Pole, put the next one on his shoulders and the next one on his shoulders and so on. And you'd need 6.5 million Einsteins to cover the diameter of the Earth. So this is roughly a step of 10 million or so to go from a human scale to the scale of a small planet. We can go out to a bigger object. This is our sun, and I guess it's kind of difficult to see with the lights, but you can do the same sort of thing, and if you want to do this in terms of Einsteins, you'd need 700 million Einsteins, or if you want to do it in terms of Earths, if you pile up 100 Earths, one on top of the other, you'll cover the diameter of the sun. And this is just one typical star, so let's go out even further and look at our solar system. So the Earth orbits the sun and roughly on a circular orbit. It's slightly elliptical, but for our purposes, we can approximate it as a circle. And the radius of that in terms of meters is 1.5 into 10 to the 11 meters, which is a very inconvenient number to have to carry around. So people who study collections of planets like our solar system, they don't like using meters to measure lengths. And they use 2 different units of lengths, so 2 different ways of measuring lengths. So one's the astronomical unit, and the abbreviation for that is the AU, and that's the average radius of the Earth's orbit around the sun. And one way to think about that is, so this thing is not drawn to scale. If it was, you'd need 100 suns in a row to reach from the sun to the Earth's orbit, so it's another factor of 100. Or if you want to use Earths and pile them up in a line to get to the Earth's orbit, you need 10,000 of them. And so it's a pretty big step, even from the scale of the sun, it's a factor of 100. So you can use AUs, or the other thing that's useful is to measure things in terms of light travel time. So light has perfected cruise control in vacuum. It always travels at exactly the same speed in vacuum. And it's a pretty high speed here. It's 3 times 10 to the 8 meters per second. And this is one place where the old British system of units is kind of a little bit more useful. If you replace a meter by roughly 3 1/3 feet, then this is 1 billion feet per second. So in a nanosecond, light travels this far, and it travels really, really fast. So it goes 1 billion feet in a second. And to cover the distance from the sun to the earth, so when you're looking at the sun, and you should never look at the sun without protective equipment, because otherwise you'd damage your retina if you did that. But when you're looking at the sun, that light that's hitting your retina now left the sun 500 seconds ago in the past. You're not seeing the sun the way it is now. You're not seeing it in the present. You're seeing it in the past. And the same thing's true in this room. If you look at the person sitting next to you, you're seeing her or him 2 nanoseconds in the past. You're not seeing that person in the present. And this is something we don't really appreciate that much because our brains don't really care about nanoseconds. They assume instantaneously you're seeing the person at the same time as you're experiencing, and it's not true. You're seeing everything in the past. So it takes 500 seconds for light from the sun to get to us on the Earth. We can take another step and go out to Proxima Centauri, which is our nearest neighboring star to the sun. And that's a factor of about 10 to the 5. In terms of meters, that's the distance from us to Proxima Centauri. In terms of light travel time, it's 4 years. So when you look at Proxima Centauri through a telescope, you're seeing it 4 years ago in the past. You're not seeing it at the present. In terms of AUs, it's about 200,000 AUs. And so it's starting to get to be a problem even with AUs. And so people who study collections of stars don't want to use the AU as a distance scale. They use a different unit, and that's abbreviated PC, and itself is, which is an abbreviation of parsec, which itself is an abbreviation for the phrase a parallax of an arc second. And this is kind of something that came out of the history of astronomy. It's a pretty strange length unit. But the way it's defined is you take this 1 AU over here, and you take your astronomer with her telescope, and you send her away very, 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 very far away, such that this 1 AU over here subtends an angle, a really tiny angle called an arc second at her. So if you go around a whole circle, there's 360 degrees, and each of those degrees can be split into 60 arc minutes, and then each arc minute can be split into 60 arc seconds. So an arc second is an extremely tiny angle, so if you want this huge distance to subtend an arc second at her, she has to go really far away. And when she's subtending 1 arc second with this 1 AU, she's said to be 1 parsec away. And for us, it's probably a little more convenient to realize that 1 parsec is 3 1/4 years or 3 1/4 light years. So if you travel at the speed of light and go for 3 1/4 years, you'll cover 1 parsec. And in terms of parsecs, the distance to Proxima Centauri, so that's 4 years away, so it's roughly 1 1/3 of a parsec away. That's kind of the spacing between stars, roughly. So to make this a little more concrete, the moon is 4 times 10 to the 8 meters, and in terms of light travel time, that's 1 1/3 second. Pluto's orbit is probably something that's characteristic of roughly the size of the solar system. That's 40 AUs, or 6 hours in terms of light travel time. And the furthest we sent anything are the 2 Voyager missions, which NASA launched in 1977. And these numbers are from 2017, the 40th anniversary. And at that point, Voyager 1 was 140 AUs away, about 19.5 hours away in light travel time, and it's gone further now. But in terms of PCs, it's about a thousandth of a PC. So it's not that far away compared to the distance to the stars. It's about 1,000th of the way to the nearest star. So that's our solar system. This one is much clearer if you look at it on the computer. I don't know if we can turn down the lights more, but it's the picture of our Milky Way. And if you go search on your favorite search engine, if you look for European Southern Observatory Milky Way, you can see this. And you can compare this to an older picture taken from Palomar. So it's a bunch of pictures, they put them together. And probably the best way to discuss this is to use the artist's impression here. So this is the galaxy we live in, and you can go out and see this if you know where to look, and it's dark enough, and if you haven't done that, you should go look for it. You'll see this big band of stars in the sky. So maybe we should start with what it looks like. It's basically a disk, like a pizza or a frisbee, and there's a bulge in the center, and if you're looking at it from the top or from the bottom, it looks like a circular disk, and you can see the spiral arms in it. And so the size here, if you want to cross the diameter of this disk, we have these numbers up here. It's 50 kiloparsecs. So kilo is 1,000. So it's 50,000 parsecs. And I told you 1 parsec is 3¼ years. So it's roughly 160,000 years. So if you travel at the speed of light, it would take you 160,000 years to cross this. And we can't travel at the speed of light. We've got to be massless. So it's things like electromagnetic waves that travel at the speed of light. And the sun is 1/3 of the way out. So it's 160,000 years across here. And you can compare that to the distance between Proxima Centauri and the sun, which is 4 years, or the distance between us and the sun, which is 500 seconds. And this is a collection of about maybe 200 billion or so stars. The sun is sort of a typical star. It's probably twice as massive as your average star. And they have mass, so they're pulling on each other gravitationally. And the fact that it's spread out in a disk tells you immediately that something else is happening too. Because if you just had gravity, so if I have a mass or something like this and I let it go, gravity is going to pull it down to the bigger mass, and the bigger mass is going to pull up also towards it. And the fact that these stars are around here and it's a disk is telling you that there's some other energy that's preventing gravity pulling them in. And that energy is rotational energy. The stars are rotating systematically in the disk. And it's like a satellite around the Earth. It doesn't immediately drop, but it keeps moving around in a circle. And the stars in here in the central region, the galactic nucleus and the bulge, they're moving around randomly. So our black hole at the center of our galaxy lives at the galactic nucleus, and it weighs about 4 million times the mass of the sun. It's actually pretty small on the scale of black holes at the centers of galaxies. Some can be 1 billion times as heavy as the sun. And we live, this whole thing is embedded in a much bigger object called the halo, which is probably 10 times as big. And that's where a lot of the dark matter is. And in this halo, we have these guys called globular clusters. These are collections of hundreds of thousands of old stars. And they're pulled together in spheres pretty much. And if you know where to look, you can see these through telescopes, and they're really nice objects to look at. And these guys are kind of orbiting three-dimensionally in the halo about the center of our galaxy. So this is our galaxy. We can walk out further and look at a neighboring big galaxy, which is the Andromeda galaxy. And this is another thing you can see if you know where to look on the sky. This is also a spiral galaxy. You can see the spiral arms, and you can see the central bulge. Andromeda is a little bit bigger. It probably takes about 200,000 years for light to cross it from one end of the disk to the other. And in terms of distance from us, it's about 750 kiloparsecs. So that translates to about 2.5 million years. So when you look at Andromeda, the light that's hitting your retina now left Andromeda 2.5 million years ago in the past. And it traveled in a straight line and eventually hit your retina. And that's kind of an interesting time scale for human evolution on Earth. Probably the most famous hominin fossil is Lucy. She lived in Ethiopia 3.25 million years ago. And apparently she was scared of predators, so one night or one day she climbed a tree. And she apparently fell asleep in the tree and fell out of it about 3.25 million years ago, a little bit before, maybe a few 100,000 or 700,000 years before light that's hitting your eyes now left Andromeda. But that's kind of the time scale for what was happening on Earth then for human evolution. So galaxies are pretty heavy objects. They contain hundreds of billions of stars, and they can pull on neighboring galaxies, and they collect together and they form what are known as clusters of galaxies. And this is a nearby cluster called the Virgo cluster, and every single spot of light you can see here is a galaxy with 100 to 200 to 300 billion stars. And you can probably see about 1,500 or 2,000 galaxies. This is just the central region of Virgo. And the scale here is a few megaparsecs. M is million. So if you want to turn that into light travel time, you multiply that few million by 3.25, and maybe it's about 10 million years to cross this traveling at the speed of light. And these are pretty huge objects, and there are many, many of them. And if you look on larger scales, this is a picture of the northern galactic pole area. It was taken by Shane and Virtanen in the 60s and made into a map by Saldner, Siebers, Peebles, and Groth. And what you're looking at here, the scale here is, so maybe I should go back and show you how this is related to our galaxy. So it's the region up here, and it's a wedge. So you can kind of think of a cone here, and then they cut it at the top and the bottom, and they're showing you that whole region and showing you all the stars in it. And the scale here at that distance from us is 300 megaparsecs across here. And so if you multiply that 300 million by about 3.25, it's about 1 billion years to cross this at the speed of light. And you can see three structures here. So there's a cluster of galaxies, there's a coma cluster, there are other clusters over here. There are voids here where you don't have any bright galaxies, so they're blacker than average. And then you can kind of see these one-dimensional filamentary structures. There's a lot of them. And so the way to think about this is to think about bubbles in your bathtub when you're having a bubble bath. And the bubbles are like the voids. The bright galaxies live on the surface of the bubbles. And where two bright galaxies intersect, you get a one-dimensional line. It's not necessarily a straight line, but there you have an enhancement in the number of bright galaxies. And those are the filaments. Because there's not that many bright galaxies inside the bubbles, they look blacker, and those are the voids. And then you have the filaments. And where a whole bunch of bubbles come together and the filaments come together, you get the rich clusters. So you can trace out these filaments. They kind of end up on the rich clusters because the galaxies kind of congregate there, and there's an enhancement. So this is a distribution that's called anisotropic. So maybe we should start out with what we mean by isotropic. So if you're standing at one point and looking around you in all directions, above you, below you, to your right, to your left, in front of you, and behind you, if it looks the same, it's isotropic. If it doesn't look the same, it's anisotropic. And this room looks very anisotropic. When you look to your right and you look above you, you don't see the same person in those two positions. It's very anisotropic. If you get 20 miles above the European continent, or maybe 30 or 40 miles, you could see the Alps, and you can see flat plains, and you can see maybe part of the ocean if you're high up enough, and it looks different in different directions. Our solar system is anisotropic. You look in one direction, you see a big bright star. You look in other directions, you don't see anything equally big and bright. The Milky Way is anisotropic. It's even anisotropic on scales of hundreds of millions of light years. You look over here, you see a void. You look over here, you see thousands of galaxies. The thing that's kind of surprising is you go a factor of 10 or so bigger in length, and it becomes very isotropic. And this is the biggest objects we can see in space right now. This is a picture of the afterglow of the Big Bang, and it was taken by the European Space Agency satellite called Planck. And they had microwave detectors, so if you've done cooking at home with the microwave oven, that's the radiation that they're trying to detect. Or if the police have given you a speeding ticket, that's because they've used microwaves on you. They bounce the microwaves off your car from a source, and they've collected the scattered microwaves. and they measure the pitch of the outgoing ones and the ingoing ones, and they can tell how fast you're going. So microwaves are part of the electromagnetic spectrum. Their wavelength is very, very large compared to the wavelength of light we see with our eyes. So they're fractions of a millimeter or so. So what they're looking at is that you have the satellite here and you have a microwave detector and you look around you in all directions. And one way to think about this is that the satellite is at the center of a beach ball and it's looking at the surface, the interior surface, and measuring the color or the temperature of the light that's coming off that interior surface. And so what I'm showing you here is I've sliced that beach ball from the North Pole to the South Pole and spread it out over the plane. So this is one edge that I cut, and this is the other edge. And if you want to reassemble it, you should take this edge and fold it up and match that edge. And we do this with globes all the time when we want to show the surface of the Earth, except we do it the opposite way. So you're seeing the temperature over here, the color. So there's cold spots and there's hot spots. And you can measure the temperature, and maybe the first thing you're interested in is the average temperature across the whole sky. And if you ask the observers what the average temperature is, they'll tell you it's about 2 3/4 Kelvin, so roughly 3 Kelvin. And the Kelvin temperature scale is the absolute temperature scale. At 0 Kelvin, motion stops except for quantum mechanical uncertainty principle motion. And this room is roughly 300 Kelvin. So this is very, very cold compared to this room. So once you know the average, maybe the next thing you're interested in is the temperature difference between the hot spots and the cold spots. And that's roughly 30 or 40 millionth of a Kelvin. So the ratio of the temperature difference, 30 millionth of a Kelvin to the average, which is 3 Kelvin, tells you how bumpy this distribution is. So if you take 30 and divide by 1,000,000 and then divide by 3 because the average is 3, you get 10 to the minus 5. Or if you turn that into a percent, it's 0.001% because you get rid of 2 powers of 10 when you're talking about this in terms of a percent. So the temperature over here is the same as the temperature over here. The temperature, the bumpiness, the delta T over T, it's the same to 0.001%. And this is very, very different than here. There's a huge difference between the number of galaxies there and the number of galaxies there. This is much more anisotropic. But over here, when you look in this direction, or you look in this direction, or you look in this direction, you're basically seeing the same temperature. So these are two really important facts about the universe. Locally, on scales close to us in our neighborhood, the matter and the light, or the electromagnetic radiation, is anisotropic in space. But when you look out at much larger scales, beyond maybe 100 million light years, then on average, the distribution of matter and radiation is isotropic in space. And the way physicists understand these now is through what's known as the inflation model of the early universe. This has not been established as part of physics yet, but all the predictions it makes are consistent with all the observations we have. But our observations are not yet precise enough to really test this model. But you can read about this if you go search on your favorite search engine and look for inflation model of the early universe. And you have to be kind of careful what you read, so it's useful to maybe go to reliable things like Wikipedia or Scientific American or the equivalent European magazines and journals or web pages. You've got to be a little bit careful what you read on the web. So, okay, so those are two facts. This is the third fact, and it's that the universe expands. And this one is even more difficult to appreciate. So if the universe expands, that means we have measuring devices, and here's an example of a measuring device that's not also expanding the same way. If the universe expanded and this expanded the same way, we wouldn't know that the universe expanded. So we've got to try to understand why this is not expanding and why we think the universe is expanding. So there's two forces that are relevant when we're talking about measuring devices this big and the universe. So the one that's really obvious is gravity. So if I have a mass here and there's the Earth's mass and I don't support this, it's going to be attracted by the gravitational field of the Earth, and it has a gravitational field and it's going to pull the Earth towards it. And the Earth moves a tiny amount. It just moves a tiny amount because it's way, way, way heavier than that little measuring device. And that's gravity. So gravity, you have two masses. It's always attractive. It pulls the masses together. The other thing about the gravity on our scales and the scales of that is that it's an inverse square law force. That's what Newton discovered. And that when you double the distance, the force goes down by a factor of 2 squared. So it goes down by a factor of 4. If you triple the distance, it goes down by a factor of 3 squared. And it goes down by a factor of 9. The other important force is the electric force or the electromagnetic force. And we know that there are positive charges and there are negative charges. And conventionally, the proton is given a positive charge and the electron has a negative charge. And there are other kinds of charged particles. But if you bring two electrons close together, the electromagnetic force is going to push them apart. And if you bring two protons close together, the electromagnetic force is going to push them apart. But if you bring a proton and an electron together, the electromagnetic force is going to pull them together. So under the electric force or the electromagnetic force, like charges are pushed apart and unlike charges are pulled together. Gravity is always attractive on these scales. Two masses always attract each other gravitationally. So the force law for charged particles under electromagnetism is also an inverse square law force, and it's called the Coulomb force. And so it's the same thing. You double the distance, it goes down by a factor of 4, and so on. So the obvious question is, if you take two protons, they're going to be pushed apart electromagnetically, and they're going to be pulled together by gravity. And you can calculate the ratio of those two forces because they're both inverse square law forces, and so the distance dependence cancels out. And if you do that, you'll find that electromagnetism is much, much stronger. It pushes apart the two protons by 36 powers of 10 more than gravity pulls them together. So electromagnetism is a really, really strong force. Okay, so I have a few more questions. So are you pulling on your neighbor electromagnetically? Okay, who thinks you're not? Can you put up your hands? 1, 2, 3, 4, 5. So who thinks you're pulling on your neighbor electromagnetically? 1, 2, 3, 4, 5. And most of you don't have an opinion? You're just really shy? Okay, who thinks you're pulling on your neighbor gravitationally? Okay, so, and who thinks you're not pulling on your neighbor gravitationally? Okay, so I guess the gravitational part is settled. So, so some of you probably combed your hair very vigorously before you came in here, right? Or brushed your hair. Or maybe you came on a bicycle. So you're made up of atoms. So atoms, well, you're made up of molecules, but it's easier to think about this in terms of atoms. So you're made up of atoms, and atoms have a nucleus that have protons with positive charge in the center, and they have an electron shell with an equal number of negatively charged electrons. So as long as you're outside the atom and you're far enough away, the electrons cancel, the electron negative charge cancels the proton positive charge, and so you're electromagnetically neutral. So your electrons are pulling on your friend's protons and they're pushing on your friend's electrons, and so they cancel out. But you can throw off that balance if you build up enough static charge by combing your hair really vigorously, and you get some static charge on you. So when you get to larger scales, as long as you're not thinking about atoms and molecules, I mean, it's kind of really interesting because if you think about an atom, the nucleus is 4 powers of 10 smaller than the electron shell, so you're basically empty space, and the stuff you're sitting on is empty space, the chair you're sitting on is empty space, and the wall is empty space. And so in principle, you should just be able to walk through all of them and fall through what you're sitting on, right? And the reason that doesn't happen is because these electron clouds don't like the electron cloud of the neighboring atom, and they push against each other, and they have nowhere to go because they have neighbors on the other side, and those clouds are all holding each other in place. And you can't penetrate them because you're made up of electrons also outside your atoms. But you're basically empty space, and it's electromagnetic force that gives you this rigidity. So the electromagnetic force is much, much stronger on the scale of this, and even on human scales. But when you look at two planets, they're basically neutral because they're mostly made up of atoms and molecules. And the gravitational force there is going to completely overwhelm the electromagnetic force. And when you get out to larger scales, like scales of galaxies, gravity is going to be the dominant force, and electromagnetism is irrelevant. But your meter stick, your measuring device, is held together by electromagnetism. So gravity is not going to overwhelm electromagnetism on the scale of your measuring device, but it's going to be the dominant force for cosmology. And so what we want to do for cosmology, if we want to talk about it, is to use our most accurate model for gravity, and that's Einstein's theory of special relativity. So Newton assumed space was fixed and that there was a uniform time and everything happened in this fixed space. He could collide his balls in it and study them. And Einstein realized that he could give a more accurate description of reality, especially on very, very large scales, or for strong gravitational fields, or things moving at speeds close to the speed of light, if he could allow space to deform and time to deform in response to what was happening. So he made space and time become dynamical and part of physics. And so that's what you have to use if you want to discuss cosmology. And unfortunately, Einstein's theory of general relativity is mostly mathematical, and you have to solve those differential equations, those partial nonlinear differential equations, and look at what they tell us. And what I'm going to do is I'm going to translate those solutions into English, and that translation is somewhat inaccurate, but I'll try that. And what it tells us is that general relativity wanders around in space, and where it finds regions slightly underdense on average, it creates new space. And that new space has to go somewhere because there's not enough space to hold that new space, and so it spreads out. And everything lives in space. And so galaxies live in this space, and if space is spreading out, they go along for the ride. And that's kind of a really difficult thing to appreciate. So I'll try to start out with a few cartoon demonstrations. And I have one here. And it's basically that picture up on the board. And if I had a few more hands, I could hold my measuring device up with it. Or maybe if you want to grab this. So I've got a wave on here. This is my space. It's an expanding band. And here's my measuring device. And I'm going to create space. And you can see the wavelength gets bigger because the ruler stays fixed, right? So the wavelength is the difference, the distance between the peaks. So if the universe expands, the wavelength gets bigger. If the universe contracts, the wavelength gets smaller. So we have light, and light has a spectrum, thank you. So blue light is shorter wavelength and it's higher energy, and red light is longer wavelength and it's lower energy. So if you expand the blue light, and you start out with blue light and you start expanding space, then it's slowly going to turn into red light if you do the expansion long enough. And this is okay at some level, but there's a couple of things that it doesn't do well. So space doesn't, you don't go to the, general relativity doesn't go to the end of space and start pulling. So what it does is it goes into space and it creates new space, and that spreads out. And space is not necessarily finite. It doesn't have ends. And this doesn't happen just in one dimension. It happens in all dimensions. So we live in a three-dimensional space here. And so I don't know how much time I have left.
15 minutes.
Okay, great. So we need to say something about the size of the universe. And so one way to think about it is think about this locally. So you should think about this exercise band going out to infinity, but this guy is pulling it just at these points. And you can call this distance roughly the scale factor. And in cosmology, that's the variable a, which is a function of time. And as time goes on, this gets bigger and bigger, and the distance between the hands gets bigger and bigger, and the scale factor gets bigger. And the wavelength, you start out, if you emitted the light over here when the universe was younger, as time goes on, the wavelength gets bigger, and so maybe it's blue here and it'll be a little bit purple here. And astronomers prefer working in what they call the redshift, which is the symbol Z or Z. And this is defined through this mathematical equation, 1 plus Z is equal to the value of the scale factor now, divided by the value of the scale factor when you emitted that light. So maybe you switch on a galaxy over there, and that's the size of the scale factor, and it'll be smaller than here. So if you go just to the present, then the scale factor here is exactly the same as A now. So this is 1 because this becomes A now, so A now divided by A now is 1, and so Z or Z has to be 0. So the redshift is 0 here. As you go back in time, A gets smaller than A now, and this becomes bigger than 1, and so Z or Z has to become bigger than 0. So Z becomes bigger towards the baby universe, while time and scale factor become bigger to the present universe. And this is kind of the expansion of the universe. So this guy was the guy who first detected this. He used this telescope. This is Slipher. And he looked at galaxies outside our Milky Way. And he found that there was this redshifting. And so one possibility is that, I mean, you've noticed this phenomenon for sound. If you've noticed a police car or an ambulance go past you, so as the ambulance comes towards you, the pitch goes up, and as it goes past you, the pitch goes down. So the wavelength's getting shorter as it's approaching you, and as it's going past you, the wavelength's getting longer. So that's the same thing that light does. It's a little bit more mathematically involved because you're traveling at the speed of light. But light coming towards you will look bluer, and light that's moving away from you, from a source that's moving away from you, will look redder, and that's why it's called redshifting. So he discovered this, and so one possibility is that Slipher, at some point in the distant past, there was a huge firecracker and it went off, and it spread all the galaxies out away from the point where Slipher was. But that's not what's happening. So what's happening is even a little bit more interesting. Oops, sorry. So this is a more accurate picture, and maybe I can start with this. So we have space expanding. So the galaxies are like these ping pong balls. And after they've formed, the galaxies do not change in size. What's changing in size is the space, the black band between them. That gets bigger and bigger, and that's moving the galaxies away from each other. And that's this picture up here. Sorry. So what we have up here is part of a flat universe. So there's 3 dimensions over here. There's one spatial dimension here, one here, and one over here. And I'm just looking at a small piece of this flat universe. So, and you know it's a small piece because if it wasn't just a small piece and you went to the edge and you looked out, it would look different than when you looked in. And we argued that it has to look the same in all directions on really large scales. So this has to go out to infinity in all 3 dimensions. And these chocolate chip cookies are, chocolate chip pieces are galaxies. So we'll place an observer on each one, and we'll ask an observer on number 3 what she sees. And she's going to tell you as the yeast rises, she sees all other chips move away from her. And you can do this with an observer on number 5, and he'll tell you exactly the same thing. So the fact that Slipher was seeing redshifts in every direction he was looking at didn't mean he was at the center of the universe. It just meant that every galaxy or every particle or every point in space was moving away from every other point in space. So the Big Bang is not an explosion at one point in space at one instant of time. It happens at an initial instant of time. Every point in space moves away from every other point in space. And it's likely that, at least in our simplest model that's consistent with all the measurements, we had an infinite number of points in space because it's an infinite space. And every one of those infinite points in space moved away from every other infinite point in space. And they're still doing that now. So after Slipher's observations, Hubble came along and he had access to a better telescope. And with this telescope, he could resolve individual stars in these galaxies Slipher looked at. And he realized that he was seeing some pulsating stars that are called Cepheid variable stars. And these stars are extremely useful because of a relationship that Henrietta Leavitt had discovered in the early 1900s. And what she had found is that the period of pulsation of these stars is related to the wattage of the star. So if you can measure how fast they oscillate, you immediately know the wattage. You'll know whether it's a 100-watt star. Well, not a 100-watt star, maybe 10 to the 43 watts or something. But you'll know the wattage. And once you know the wattage, you can figure out the distance. So Hubble used these Cepheid variable stars to measure the distance. And Slipher used Doppler's formula to get the speed at which these galaxies were receding. And so Hubble ended up with the Hubble law that the speed of recession was proportional to the distance to the galaxy. And it's a linear relationship. So a galaxy twice as far away was moving twice as fast. A galaxy 3 times as far away was moving 3 times as fast. And this constant of proportionality is the Hubble constant. And you can see the data here. This is a pretty famous plot. It's from Wendy Friedman's group, and she was one of the main investigators on a key project for the Hubble Space Telescope. And this is from 2001. So the Hubble Space Telescope, this was one of the reasons it was designed to measure the Hubble constant more accurately than had been done previously. And we have the recession velocity, recession speed on this axis, 10,000 kilometers a second, 20,000 kilometers a second, 30,000 kilometers a second. And the distances to these galaxies, they're also up here, but the numbers are down here. This is 100 megaparsecs. So a galaxy 100 megaparsecs away is moving at about 7,000 kilometers a second from us. A galaxy 200 megaparsecs away is moving away at about 14,000 kilometers a second. And this straight line was the best fit to the data then. And this is Hubble's law. V is proportional to R. And this is the expansion of the universe. And maybe I should probably stop here, I guess. Okay, so we can go on and look at this. We have the expanding universe. So there's special observers here in the expanding universe. So you can think about observers at rest with respect to the expansion in contrast to observers who own a rocket and are moving. So observers who own a rocket and are moving will also notice a Doppler effect, just like when the ambulance is moving relative to you. If you were moving relative to the ambulance, you'd notice the Doppler shift. And so these observers who are moving relative to the expanding universe will not see an isotropic universe. But those who are at rest, and they're called cosmological observers, this is a generalization of what Copernicus told us, that we're not privileged observers. So our friend on Andromeda or some other galaxy, if we asked her what she would see when she looked on large scales, she would tell us that she sees it's isotropic. So the experiment you've done is you kind of moved from here and you noticed it's isotropic there, and you moved over to Andromeda and you've noticed it's isotropic. And there's a theorem in geometry that then tells us that we actually live in a homogeneous distribution. And that again is some jargon, but the easy way to think about it is to think about a big container of milk, and you put your scuba suit on and you jump into it. And you swim around in it, and no matter where you go, it's going to look exactly the same white as long as you don't get to the edges. So that milk is homogenized, and it's homogeneous. It looks the same. You can translate yourself in space, and it looks the same. And that has much, much more symmetry than isotropic about 1 point. And that makes cosmology easier to do. And it allows us to restrict ourselves to 3 geometries. So we live in a 3-dimensional space. There's a vertical axis here and 2 horizontal axes here. but I can't draw three-dimensional universes on here, especially for the curved cases. So I'm going to draw two-dimensional ones. I'll suppress one space dimension. And the first one is the flat one, like the top of this table. But again, it's got to be infinite, because if you walk to the edge and you look out, it looks different than if you look in, and that's not isotropic. So this has to be infinite, and it goes out in both directions, and it's flat, it's zero curvature. The other one is the closed geometry. It's the surface of the sphere, and you can think of yourself as an ant on it. And as time goes on, it gets bigger and bigger, and that's closed and positive curvature, or you can have the open one. And maybe I should just stop with the toy model of the expansion in a closed geometry, and I'll do that over here. And maybe we should have, you can hold this, I can do this. So I think this is on. Okay, so you've got to think of yourself as an ant, and all you do is you live on the surface of this balloon, and the galaxies don't expand. What's expanding is the space created between them, and it gets bigger and bigger. And you should ignore this, and you should ignore the inside, you should ignore the outside. And so if we live on this galaxy over here, and look at light from this galaxy, it takes time for that light to reach us, and in that time, the universe, the space has been created here, it gets a little bit bigger, and if this light starts out blue, maybe it'll get a little bit of a purple tinge. And if you go to a slightly further away galaxy, it takes longer for that light to reach us, and more space has been created, and it'll be even more purple. And you can go to a further away one, and if it continues for long enough, it'll eventually become red, and then further away it'll become infrared. And that's why James Webb is really useful. I guess we got a bit of a leak here. It doesn't like the pressure.
The other microphone.
Oh, you're getting feedback. So if it's infrared, they're much further away, and the James Webb Telescope has an infrared detector, and so it can see galaxies further away. So there is no preferred center. Every galaxy moves away from every other galaxy, and the further away you're from a galaxy, the redder it's going to be. And yeah, maybe I'd better stop here. I'd be happy to answer any questions.
Professor Ratra.
Thank you.
And we have a couple of minutes left for questions. So feel free to ask questions in English or in Slovak, and somebody will translate. If you have questions but not enough English knowledge, go ahead.
Have you ever had to explain this to airport security?
A couple of times. Yeah, I don't know if this is still on, but I've never said it's a demonstration of a Big Bang.
There was a question.
It seems to me that dark energy and dark matter are kind of the scientists try to kind of find these issues, but like only small part of scientists try to modify general relativity.
Yes.
So it seems to me that there is a general kind of confirmation bias towards general relativity, and it seems like scientists are afraid of losing job when challenging general relativity.
Well, I don't know if that's really a fair characterization. So general relativity, I mean, that's the reason we went and talked about homogeneity. It has much more symmetry, and it makes it much easier to work with the models. And so one thing you could say is, why do I believe in homogeneity, and why don't I just look in some arbitrary cosmological model from general relativity? And the reason is, I mean, we have some good observations that support homogeneity, and it seems to fit most of the data. And the same thing's true about general relativity. We know it works very, very well on small scales for black holes and gravity wave emissions. I mean, the spin-down rate's exactly what you'd get from Einstein's theory, and that's been confirmed by all the LIGO measurements. It works really well for binary pulsars. It works reasonably well for the microwave background on much, much larger scales. So why should we assume that it doesn't work on intermediate scales where we see dark matter and dark energy? So dark matter, the situation is much clearer. So people have tried modifying general relativity, and this is not the first time. So even when galaxies were first discovered in the 1920s and the 1930s, the observers were making mistakes about how fast they were rotating, and people suggested then that maybe Newton's inverse square itself was wrong, which is the same as saying that the theory of gravity was wrong. And a lot of people tried to modify it, and they couldn't get it to work. And more recently, people have done the same thing with dark matter, that maybe inverse square law is wrong, but they haven't succeeded with that. The thing they've succeeded with modifying Newton's F equal to ma. And what they say is that the accelerations you're seeing where you're seeing dark matter are so much smaller than you experience in everyday life where you've tested F equal to ma, and maybe it's not unreasonable to think F equal to ma doesn't hold for small accelerations. And this is a program that's called MOND, or Modified Newtonian Dynamics, so you can go read about it on Wikipedia. And it works really well for spiral galaxies like ours. But the problem is that for each galaxy, you've got to decide at what critical acceleration F equal to ma changes. And it's not the same for the Milky Way and for Andromeda. So I don't know if you'd be comfortable living with the fundamental law like F equal to ma that depends on where you live in space. And the other problem with MOND is it can explain dark matter on the scales of galaxies, but it fails on the scale of clusters, and you have to reintroduce dark matter there. So even if you fix it in the Milky Way, you can't fix it in the Coma cluster. So it's not that appealing in that sense. And people have tried to modify general relativity to explain dark energy, and you can do it, but there's no particular motivation for that kind of model. But when you modify general relativity by adding dark energy to it, it's consistent with the amount you measure using half a different observational techniques. You can measure it using the supernovae, you can measure it using baryon acoustic oscillations, you can measure it using the microwave background, and they all give you roughly the same amount of dark energy. So it's kind of reassuring, because if each of those tests gave you a different amount of dark energy, then you'd probably throw away dark energy also. So I'm not saying that general relativity is correct, but there's no strong evidence that you need to modify it right now as long as you put in dark energy.
Okay. First question? Yeah. I have a hard time just grasping the concept of space. Like, does it mean like is it like a net of atoms, or how do the...
No, it's a part of reality, and it's just a way of ascribing distances to points in space. So you set it up by saying that there's some rule that tells you how far you are from me, and that depends on a bunch of variables, and this distance could be time dependent. And then Einstein's theory of general relativity is kind of set up that way, that it tells you how the distance between you and me changes if we're very far apart and there's gravity only, or if there's electromagnetism or there's some other force, it'll tell you. So it's a generalization of F equal to ma to an equation that basically tells us how we move. And if there's a strong gravitational field, space is going to be curved. And if we're just kind of walking in straight lines parallel to each other, we can't do that when there's a strong gravitational field. We'll either come together or we'll move apart. And it's just a way of predicting how we move, just like F equal to ma. Do you know how to integrate F equal to ma? No, okay. So a is the acceleration, and so when you integrate that once, so if we're just talking about our relative acceleration, we integrate that once, it'll tell us how fast we're moving towards each other, and you integrate that once more, it'll tell us whether we're coming closer together or we're moving apart. And Einstein's general relativity just improves upon that and makes it more accurate for very large distances or very strong gravitational fields or things that are moving at close to the speed of light.
More questions?
Maybe I want to also ask about space, because if space is inflating, why are there some points, for example, galaxies, which stay in couples? Because intuitively, I'd say that each point moves away from every other point. Right. But why are there some?
Why are some of them not? Okay, so you're not increasing, and the table in front of you is not increasing, and the reason is the electromagnetic force is much more important and it dominates. So galaxies are not increasing because the Newtonian part of gravity, the 1 over r squared part, is a very accurate description of them after they're formed. And the Einstein space creation process is not strong enough. So if you kind of think about this, this is again a little bit inaccurate, because if you just look at two galaxies over here, if they're close enough together, the Newtonian gravitational attraction between them is pretty strong, and they should actually be moving. So I couldn't give you a demonstration like that. These galaxies are not all of them are fixed. They're going to be pulling their neighbors together, and that's one part of gravity. The other part is the space creation part between here. And so if you have a lot of mass in these guys, then they're going to pull together stronger than the space creation can push them apart. And between us and Andromeda, we're actually being pulled together by gravity, and Einstein's space creation process is not strong enough to push us, the Milky Way and Andromeda, apart. So it depends on what scales you're talking about. On very large scales, the space creation process dominates, and on smaller scales, your intuition, the ones you've developed thinking about Newton's laws, are correct.
Any more questions?
Maybe I have one. So at the beginning of the presentation, you said that dark matter is located in the halo around the galaxy, and I was thinking that dark matter is like distributed throughout whole galaxy. So
yeah, it's distributed throughout all the galaxy. Too, it's more concentrated in the halo. It's a little bit more concentrated in our galaxy, but it's distributed in between galaxies also. And it kind of bunches up a little bit near where you have stronger gravitational fields. So dark energy doesn't do that, because if it's made up of particles, these particles are very, very light, and dark energy is very relativistic, and it starts bunching up only on scales of hundreds of millions of light years, while dark matter can bunch up on scales of tens of hundreds of light years. And dark energy is distributed much more smoothly than dark matter.
We have time for one more question.
Thank you for the presentation. I'm just interested when the galaxies are moving further away from each other. Is there like only void between them, or what's filling the space in between them?
Sorry, I didn't get the last part.
When the galaxies are expanding, like moving,
When they're moving apart.
so the space in between, there's just void, or like what?
So yeah, it's basically, so it depends. I mean, you could have smaller galaxies surrounding the bigger ones, and those could be moving apart too. And at the absolute edges of the galaxies, sometimes the space creation process is more dominant, and it can kind of pull stuff out a little bit. But they're typically moving apart as chunks, and more space is being created there. You're welcome.
Wonderful. So let us thank Professor Ratra for a wonderful presentation.
Thank you.